Welcome to the world of computer networks. Finally, we came to the last technique of error detection that we will see together. If you want more error detection techniques, you will find them in the description below. So in this session, we will talk about the cyclic redundancy check, also called the CRC. So let's start with the outcomes. Upon the end of this session, you will be able to know the types of error detection techniques and also understand the CRC and when and how it's used. We have seen in a previous video that there are basically three types of error detection techniques that are used in data communications. The first was the parity check, the second is the checksum, and the third one is the cyclic redundancy check or CRC. So let's focus on the CRC. The CRC technique is widely used in today's computer networks. It allows to control pieces of data of variable length, which means no constraint about the length of the data to be controlled. The CRC is simple to implement in hardware, and finally it has a very good error detection capabilities that we will analyze together. CRC codes are also known as polynomial codes, since it is possible to view data to be sent as a polynomial whose coefficients are the zeros and ones values in the data. So here is an example. A block of 6 bits, 1, 1, 0, 0, 1, is seen as a polynomial m of degree 6 minus 1, which is 5, with binary coefficients. So m equal x to the power of 5 plus x to the power of 4 plus x to the power of 0. Why we don't have x to the power of 3 and 2 and 1? Because we have here 3 zeros. So this is the polynomial representation of our data. We can divide the CRC operation into two parts: the CRC generation at the sender side and the CRC check at the receiver side. So let's look at the CRC generation. Formally, the CRC generation involves basically 5 steps. Step number 1, find the length of the divisor that we are naming here as L. After that, in step number 2, we are going to add L-1 zeros after the least significant bit to the original message. If L equal 5, for example, we will add 4 zeros to the original message. Step number 3, we perform a binary operation or a binary division operation. So here, all CRC calculations are done in modulo 2 arithmetic without carries and without borrows. This means that addition and subtraction are identical and both are equivalent to the exclusive OR of the operands. So here we recall that the exclusive operation of two operands A and B is as follows. If A and B are the same inputs, either zeros or ones, the exclusive OR is equal to 0. And if A and B are different, the XOR is equal to 1. So this is the logic behind the XOR, which is quite simple. Now, after performing the division, the operation will generate two results: a remainder and a quotient. So the remainder is what we are looking for, and this is our CRC. So the CRC is the remainder of the binary division. The final step is to append the CRC that we found in step 4 to the original message before transmission. Let's see an example to explain more these 5 steps. Suppose that we want to transmit this data 100, 100. So this is our data, and the divisor is 1101. So this is the data we want to transmit, and this is the divisor. We recall the first step. So what is the first step? The first step is to find the length of the divisor. The length of the divisor is equal to 4. L equal 4. So what we have to do, we have to add 3 zeros to the original message. How many times it is going to divide? 1 time. So 1101 one time is 1101. Now let's perform the XOR operation. For same input we'll be getting 0, for different inputs we'll be getting 1. So here we have the same input, we are getting 0, here same input 0, and here we have different inputs, we have 1. We will ignore the last bit since it has no role to play in the operation. Now we will continue the operation by bringing the next bit. Again, how many times 1101 will be dividing 1000 one time? So 1101 one time is 1101. The same thing here, different input we have 1, same input we have 0, and so on. We will continue in the same way until the end of the operation. Finally, we are getting the reminder, which is 001. As we told before, the reminder is the CRC code. So this is our CRC code. What we'll be doing with this code will be appended to the original message to get the transmitted data. So here is our original data. This is the CRC. So the transmitted data is the combination of the original data and the CRC. Now, let's see what the receiver do. Once the data is received, the receiver has to check the CRC. The receiver performs the division of the received data by the divisor. So we recall here that the divisor is previously known by both sides, the sender and the receiver. Now, when the receiver performs the division, he will check the reminder. If the reminder of the division is 0, it means that no error is detected and the message can be accepted. If the reminder is anything else, which means if it is different from 0, it means that there is at least one error and the data is rejected. Finally, we can say that many international standards have been defined for different generators or different divisors. We have 8, 12, 16 and 32-bit generators in the standards. For example, we have the CRC32, which has been adopted in a number of link-level IEEE protocols and uses as generators of 32 bits. And this is the value of the CRC32 bit. The CRC can detect burst errors fewer than 32 bits, which gives very good results. That is, guys, if you like our content, please don't forget to subscribe into the channel and to like and comment. Thanks for watching and see you in another video.